Okay, following on from the marching cubes explanation, once you've run marching cubes on a medical image, you always end up with just a large number of triangles. So typically people will try to reduce the number of triangles, and the broad class of algorithm is called decimation algorithms or mesh decimation. To do this, in a simple case, you just find a point that you can delete without altering the shape too much, but it does require a little bit more thought. So the level of detail that I want to go into is kind of as follows. For this example, I'm on these course notes. I went back to VTK and I looked at the decimation algorithm in VTK, mainly because I've used this, as it were, for many years, so it's perfectly sufficient for everything I need to do, and I haven't really had to bother going back to the literature and finding an alternative. I'm sure there's lots of people out there who spend their career doing research in graphics, but for the people that just want to use an algorithm, it's quite a relatively well-established field now. And you can basically just find whatever one you can find in whatever software package, at least for most applications. So this one was done by Will Schroeder, who's actually one of the founders of VTK when they worked at, so Bill Lawrenson did the marching cubes and Will Schroeder did this mesh decimation algorithm. So if we look at this picture now, if you imagine you've got a bunch of triangles now and they're all kind of connected together, the first thing the algorithm does is categorize them into different, so each point needs labeling as whether or not it's a simple point, meaning that it's just connected to a certain number of neighbors, in this case 6. When you're removing points, you generally have to remember that most surfaces are a sort of two-dimensional manifold in a three-dimensional space. But some surfaces obviously self-intersect and things like that. So they have a category called complex. So here this point in the middle is connected to these 6 triangles in black, but also 1 triangle in red. So they call that a complex case. Forgive the hastily drawn diagram, but the next category along is called boundary. So essentially, if a point is on the edge of a surface, so you've got triangles on one side but not on another, they call that's an edge case. They've actually, in the original paper, they've got 2 more cases here. It's drawn in black and white, so it took me a while to understand it. But if you imagine, I've got this middle point here, and I've got these triangles here, but this is the top-down view. If you look at it from the side, I've added this here. If you imagine this, these 2, well, actually that should be a 3rd triangle. These 3 triangles, if they are bent over such that you're forming essentially an edge. So this is the top view, and this is the side view. Hopefully you can see my mouse pointer. So they had an edge case, and similarly they also had a corner case where you've got essentially the vertices come together to form a corner. So once you've classified your points, you can then incrementally sweep through the whole data set and work out which ones you can delete without causing too many problems. So in slightly more detail, if you imagine that in this simple case up here, for a given point, if you find its immediate neighborhood, and let's just say if those points in the neighborhood fit to a plane, roughly you can assign them within a tolerance to a local plane. You can then compute the distance of the point of interest, this middle point. You can compute the distance from that plane. If the distance is below a threshold, i.e. it's pretty much on the same plane, you can get rid of that point. And you can then, obviously, this is drawn for 6. But in the general case, once you've decided that a point is pretty much replicating the geometry of the things around it, you can then look at the first of all delete that point, but also look at the neighborhood around that and then re-triangulate the whole area using fewer triangles. Similarly, I've drawn this boundary one here. You can take these two edges here and you can work out how far away they are from this straight line here, and as long as this point is within a certain tolerance, you can say, well, actually this whole shape simplifies. I can remove that point and I can remesh the points around it. So looking at all of the cases, and I'm summarizing the algorithm somewhat, and over the years little tweaks get added for optimization purposes, but the process is basically you classify them all, and then, for example, complex points you would never delete. Edge points and corner points, you'd probably have a parameter where you say this is a feature, it's a feature that I must not remove. For example, if you had a point, a nice mesh of a table, you know that corners are at the edge, or edges and corners should be around the edge. Anything that looks like a feature in the middle of the table is probably a flat surface, so you can remove them. So you've probably, even if you've got noise on your surface, you can deal with that. So edges and corners you could remove if they're if the angle that you're looking at, labeled as alpha here, is below a certain threshold. And then the simpler cases, like this simple and boundary case, you just remove a point if it's below a certain threshold. I think in practice, when they come to implement this, they typically set up a queue structure, so you kind of give each point a score based on how suitable it is for removal, and then at each iteration you would remove the certain top percentage from that queue. So this should give you an overall idea of decimation. The reason I'm not going into any more detail is simply because I, as it were, for the last 20 years have never needed any more detail than that. All I know is that it removes certain points and tries to preserve points, sort of corners and edges, and in case where you're self-intersecting, those points never get removed. So in a nutshell, that is how the VTK decimation algorithm works. I'm sure there's plenty of others, but this one is a kind of go-to. It's built into MITK. You'll probably find other algorithms, other software packages that are built on top of VTK will be using this algorithm. Moving on now slightly, once you've removed points, you can also smooth points. So I looked through the code actually for this, and then I looked around the internet, and there are loads of different methods, but I found these Stanford notes. I've provided a link to them. I haven't checked how I'm meant to acknowledge them. I'll come back to that. But the method in those notes seemed to make sense with this diagram and also cross-referencing the code. So again, this is one method of many that you could do smoothing of a surface. I'm sure, again, there's plenty others, but I've never yet found that I've ever needed to go and do them. I think in computer-aided surgery, there's plenty of other things to be working on, such as tracking, calibration, and registration. This is an interesting part of computer graphics, but it's not one that I spend most of my life doing. So if you look at this diagram now of smoothing, these Stanford notes make quite a good point that it's easier to understand in 2D than it is in 3D. So we start off with this line diagram. So if you imagine you have this line here written in black, and you're debating whether or not, how to process this point PI here. It has, well, if you're looking from the inside of the curve, I guess, well, to the right is PI plus 1 and to its left is PI minus 1. So either way, if I'm traversing round the curve this way, this is the point before that one, and this is the point PI plus 1 is after PI. Therefore, I minus 1 plus this point plus this point divided by 2 must give you the average point here. Then if I do this point minus that point, you end up with a vector which tells you basically how to move this point, pi, to this midway point. So you can see that if I move this point here, the curve would be smoother. I'm hoping that makes sense. Again, it feels like I'm talking to myself. So if I went round, so if you imagine I had this line and I created a copy of it, I then worked out for each point where it could move to, and I applied those offsets to the new mesh. The mesh would incrementally evolve towards a smoother shape because you're averaging the points in the local neighborhood. Specifically here, given a point here, you're just looking at one point either side of it. This thing then extends to 3D. So if you look here, I've got 4 points. I haven't drawn this as a tetrahedron because you get too many lines in the way. So given pi, this point here, which is, if you can imagine this shape was actually a plane, then this point stuck up here would be quite a noisy point. It's quite a long way from the plane. So the question is, can we smooth out that noise? So we've got pk, pl, pm and pn. So we can say here n subscript I is the set of these indices. So effectively it's the set denoting the names of these points. So I've got 4 points, I've got 4 indexes in this set, and we're doing the same thing here. We're taking the average of these points. So just like in this 2D case where I'm simply taking the average of these 2 points here, this is a summation and dividing by the number of points. So this is the equivalent of this. So this is find the average point. So the average point minus this point of interest pi here gives you this vector in black. So again, in 3D, what I'm doing is I'm taking the surrounding neighborhood, in this case 4, but it would apply to any size neighborhood with any number of points, and I'm going to apply an offset. I'm going to move a point by I'm going to move a point towards this average point. So the formula to do that applies a weighting factor. So you don't have to move the whole way there. You could just say it's lambda, a bit like a learning rate in optimization. So given this vector, I can move this point by a certain percentage. The reason you might not jump the whole way is you're going to apply this iteratively over a whole mesh. So you might want to evolve it slowly, piece by piece. You don't want to move the points around too quickly relative to each other. It turns out that this differential, this averaging here, it's equivalent, as they say, if you look at the maths, to a discrete version of the Laplace operator. So you can think of this as Laplacian smoothing over a small neighborhood. But in my simple mind, because you're just computing the average position of the 4 surrounding neighborhoods points, you are effectively just moving towards the average. That's probably the way I think about this most often. So given these two things now, we now know how to, and the previous marching cubes, we now know how to segment something, how to create an isosurface, how to do mesh post-processing, specifically how to reduce the number of points and how to smooth the points. It just occurred to me as I said it, one last thing. You can run marching cubes without segmentation. You just extract whatever isosurface, but as we can see here, you end up with bits inside. So this is why I put them all together. Typically people will segment, or they will label the voxels that they are interested in. which is why up here I did a segmentation example. But be aware then that you're running the marching cubes on a binary volume, which tends to give very steppy edges. It then becomes more necessary to do smoothing. But either way, these are the tools that you would typically need to do some surface-based visualization for the purpose of computer-assisted surgery. And you probably don't need much more detail than that for now. Thank you very much.